In this lecture, we discuss some properties of Artinian rings. So the first proposition is that in an Artinian ring, every prime ideal is maximal. Now, if every prime ideal is maximal, then the curl dimension would be 0. So let us prove this proposition. So you start with the prime ideal in ring A, and we want to show that A modulo P is a field. So then P would be maximal. So that is, we want to take an element A in this A modulo P, and then for every such element we can find an inverse P, and we want to show that AB is equal to 1, which would imply that A is a unit. So we want to go from here to here. Now consider this chain of ideals. A contains A square and so on. So this chain would eventually become constant because this A modulo P, this is an Artinian integral domain, precisely because A is Artinian. So if you modulo P out, this will also be Artinian, simply because the lattice of ideals in A will descend to lattice of ideals in A modulo P, and all those ideals contain P. So thus this chain will become stable at some high power n. So at that power n, we will have this an would be equal to an plus 1 and so on. So that is, an would be equal to an plus 1 times b for some b in A modulo P. And now do the cancellation. We will get A times b is equal to 1. So which implies that A is a unit. The cancellation makes sense because we are working in an integral domain. We are starting with P as a prime ideal. So now we come to proposition 2. Here we are saying an Artinian ring has only finitely many maximal ideals. So consider a minimal finite intersection of maximal ideals. So you take finite intersection of maximal ideals and you consider minimal of all of them, and you can find this minimal precisely because we are working in an Artinian ring, and in an Artinian ring you can find the minimal element. So this minimal element is m1 intersection m2 all the way to mn, and in fact these are the precisely maximal ideals in the Artinian ring. So these are precisely the maximal ideals. So again we are considering a minimal set of minimal from the finite intersection of maximal ideals. Now this minimal set would lie at the bottom, so everything is on top of it. So say this set is S, this is say S, and this lies at the bottom and everything is on top of it. So any element lying in the minimal finite intersection will lie in all the maximal ideals of the ring A. So what we are going to do is we are going to start with some maximal ideal m in A, which is not this m1 m2 to mn, and then we are going to find a product a1 to an which lies in intersection of all these maximal ideals but does not lie in M, and that will give us a contradiction because any element which lies in the minimal finite intersection will lie in all maximal ideals of the ring, and here we will show that a1 times a2 all the way to an lies in this intersection, but it does not lie here. So let us hash out the details. So let M be another maximal ideal which is not equal to any of the mi's here. So then for each I we can choose an element ai which lies in this mi but does not lie in M. So mi minus M. So now you can form the product. So this product would lie in m1 intersection m2 all the way to mn. But this product does not lie in M because none of these ai's lie in M, and M we are choosing to be a maximal ideal, and therefore M is prime because all maximals are prime. So since none of these ai's lie in M, their product would also not lie in M since M is prime, and this is precisely the contradiction we were looking for, and therefore you cannot have a maximal ideal M which is different from all these mi's, and the contradiction is right here because any element lying in the minimal finite intersection will lie in all maximal ideals of the ring A. So proposition 3 is, in an Artinian ring some power of nil radical is 0. And this is also true for Noetherian ring, and which we have shown before. So this is also true for Noetherian ring. So since we are working in an Artinian ring, you can consider this descending chain of ideals. This nil radical n contains n square and so on, and eventually this will stabilize because we are working in an Artinian ring. So n to the power of n is equal to this nil radical to the power of n plus 1. So for some large n. Now we want to show that this nil radical is 0. So we are going to assume that this power of nil radical is not 0 once it stabilizes, and this should lead us to a contradiction. So this should lead us to some contradiction, and that's what we were going to show. Now once it stabilizes, we say that this is stable value is non-zero, then there is some element a in the ring A such that a times this n to the n is also not 0. Now we consider all the ideals generated by such elements A, and then we can choose a minimal ideal, and we can choose a minimal ideal precisely because we are working in an Artinian ring. So we can choose a minimal element and say B is the minimal element, and this be generated by a single element B, because we are just considering these ideals generated by single elements, which you multiply by n to the n will not be 0. So out of all these ideals, we choose the ideal which is minimal. So now you can see that for t greater or equal to n, so after it stabilizes, Bn to the t times nt, this will be Bn 2t, this will be again time Bnt, because it has stabilized. So once it has stabilized, for t greater or equal to n, this is same as this. So now you can see that this Bnt would lie in the ideal generated by B. So this we can say Bnn, because its stability occurs at n. Bnn would lie in ideal generated by B. But this is anyway the minimal. So this is anyway the minimal ideal. So minimal ideal for which you multiply will give you non-zero. So it's minimal ideal of this form. So therefore this Bnn is precisely generated by B. Or you can say this you can rewrite it as B is equal to Bx for some x in n to the n. So this x you are taking from here. So Bx is equal to some B here. So now you can say B is equal to Bx. Now multiply both sides by x, you get Bx equals to x square, and so on. And finally you will get B times 0, since x is in the nil radical, so x to some power m is 0. So this gives B is equal to 0. So this contradicts our choice of B, because B was chosen out of elements like this, a times n to the n, which is not equal to 0, and it was minimal such element. So there has to be a not equal to 0, but here we are getting B is 0. So therefore it has to be the case that our choice of n to the n not equal to 0 is not right, because we have a contradiction. So therefore n to the n is 0.